So we just finished chapter 3 and started chapter 4, but you guys have a test coming up this weekend on chapter 3, which was on continuities and derivatives. And so today we're just going to spend some time reviewing over what we have already done. And so you need to remember how to take a limit of an equation, and you need to know how to take a limit looking at a graph. And so remember, there's a limit exists if the left-hand side is equal to the right-hand side. And so if we're looking at the following, let's just review. The limit as, let's say, x is approaching 3, x squared plus 2x minus 15 all over x squared minus 9. So when taking limits, and we're taking a limit of this equation, what we're going to do is we're going to go in and we're going to plug in 3 wherever we see an x. So doing that, we get back 3 squared plus 2 times 3 minus 15 all over 3 squared minus 9. So simplifying this, we get 9 plus 6 minus 15 all over 9 minus 9, and we get 0 over 0. So if it gets something back in this form, 0 over 0, infinity over infinity, this is where this is an indeterminate form, and that's where we have to go back up and manipulate. So it depends on what you were working with, and on our case, because it's a rational function, a polynomial divided by a polynomial, try factoring. And so we have a trinomial looking for two numbers that multiply to give us a negative 15 and add to give us that 2. So that would be a positive 5 and a negative 3. So x plus 5, x minus 3. And then the denominator, we have a difference of squares, x squared minus 9. And so that factors as x minus 3, x plus 3. So we have two factors that are in common. And so we can cancel those out. And so now really we're taking the limit as x is approaching 3 of x plus 5 all over x plus 3. So go do the same thing, go in, plug in 3 wherever you see an x. So we got 3 plus 5 all over 3 plus 3. So we have 8, 6, which reduces down to 4/3. Not too bad, hopefully. So if you have a limit as h approaches 0 of 2 all over 5 plus h minus 2 over 5 all over h. So again, we're just going to go in first, always start and by going in and substituting. But again, when we substitute this in, we get 2/5 minus 2/5 all over 0, and we get 0 over 0 again. So we need to go back and manipulate. Well, this is a complex fraction, fractions within fractions. And so if that's the case, let's get rid of the complex fraction. And we can do that by multiplying by a fancy one. And that fancy one, we want to clear these denominators. So we're multiplying that numerator and denominator by our LCD. So that's going to be 5 all times 5 plus h. So when we distribute, notice the first piece, when we distribute to the first fraction, the 5 plus h cancels, and you're just left with that 2 all times 5 minus, we distribute to the second fraction, we have that 2 still, but the 5's cancel, and you're left with the parentheses 5 plus h. All over h times this 5 times this 5 plus h. So simplify. So we get 2 times 5 is 10. Distribute our negative 2, we get negative 10 minus 2h all over, I'm going to write it as 5h all times 5 plus h. So notice these 10s cancel. And then we have in the numerator an h, negative 2h. And in the denominator, we also have an h. So those are going to cancel with one another. So we have the limit, h goes to 0 of negative 2 in our numerator, all over 5 times 5 plus h. So we're going to go in, and wherever we see an h, we're going to go back in and we're going to plug in 0. So you have negative 2 all over 5 times 5, or negative 2 over 25. I'm looking for one other type for you guys where you again might get, here we go. So right now we're kind of looking at all those cases that you could get we're getting the indeterminate form and going back and manipulating. So right now what is in front of me is the test that I've made so far. I'll probably go back and change a little bit of it. And when I printed it off, it scrambled all the problems. So they're not in order. So the next one, limit as x goes to 81. We have the square root of x minus 9 all over x minus 81. So again, if you go back in there and you plug in the value, in this case 81, wherever we see an x, notice we get square root of 81, which is 9. 9 minus 9 is 0. So we get 0 over 0 again. So if you're looking with a rational function and it has a radical in there, then try multiplying by that conjugate, that fancy one, but using the conjugate of the square root of x minus 9 in this case. And the reason why we're choosing the conjugate is it would be in the form of a minus ba plus b. And we know that that is a squared minus b squared. And so we could just square the square the first term and square the second term. It falls out. Squaring a radical, the radical goes away. So doing that, we have square root of x squared, which is just x, and we have minus 9 squared, which is 81, all over x minus 81, all times that square root of x plus 9. But notice that what we have in the numerator, x minus 81, is a factor down here in the denominator, so those are going to cancel. So you're left with a 1 in the numerator all over the square root of x plus 9. So when we go in there and plug in 81, wherever we see an x, we get 1 over the square root of 81 plus 9. Square root of 81 is 9, so in the denominator we have 1 over 9 plus 9, or 1 over 18. Trying to find pictures. There we go. Okay, so next one, you have a picture of a graph. Okay. So I have a point kind of going through the -2, shooting downwards. X-axis at -2. -1, 1. We have an open circle. It comes back down. And then at 1, we have a value at 2. -2. And it stops. And at 1, 1, we have an open circle. And it comes like this. Okay, so this is a graph of f of x. And then it wants us to find part A, the limit as x approaches -1, and the limit as x approaches +1. Okay, so to show that a limit exists, we want to show that the left-hand side is the same as the right-hand side. And so notice as we're coming into -1, so follow the graph on the left. If we're following the graph on the left, we're looking at what y value are we getting closer and closer to as we get closer and closer to -1. We don't have to actually be there, but we're getting closer and closer to 1. So if I look at the limit as x is approaching -1 on the left, and so we denoted that with what kind of looks like an exponent of a negative of f of x, this is equal to 1. But if we also look at what's happening as we're coming in on the right-hand side of -1, we're also approaching that y value of 1. So kind of put that positive, what looks like an exponent. And so since these are equal to one another, the limit is equal to 1. But it's different when we're looking at positive 1. If we're coming on the left-hand side of positive 1, the y value that we're getting closer and closer to, and actually hit in this case. So 1 on the right, the y value that we're getting back is -2. Where if we're approaching it on the right-hand side, oops, did the wrong symbol there. That's a negative on the left. And 1 on the right, we're getting back 1. And since these do not equal each other, we can say that this limit does not exist. Okay, so I realize when you're taking this test on My Math Lab, that really you could look at this and you can do this without showing really that. You can look and say, oh, I can see that the limit as x is approaching -1 is 1. And I'm okay with you doing that without showing me any work. And I can see that you can probably see that the limit doesn't exist. But when it comes to the time when you guys actually take the test over this material in class, I want you guys to show me that step, that written work, that, hey, the limit doesn't work or exists, or it does exist because the limits are either coming in and coming into the same y value or not coming into the same y value, and explain why. If this asked, let's just even extend this further. So find where f of x is continuous. Okay, so it's continuous, right? Everywhere except for -1 and 1. And so it's continuous everywhere from -infinity all the way till we hit -1, but not include it. So put parentheses there. Union, we're hitting all the values between -1 and 1. And then union, everything from 1 to infinity. So you should be able to show why something is not continuous at a particular value. So we can show that it's not continuous at x equals -1. Well, in this case, it's because it's not defined. There's no, this is an open circle, and there's no point above or below it. So right there, f of -1 is undefined. Doesn't exist. And so if that's undefined, there's no way that this is equal to the limit. So that doesn't equal to the limit as x approaches -1. And we said it was not continuous at +1. That function actually does exist at f of 1. You go back up here, you have a solid circle when x is 1. That value is equal to -2. The problem that exists is the condition doesn't hold that the limit exists. But the limit as x approaches 1 of f of x does not exist. And because of that condition, it's not continuous there. So let's say you're given that the limit as x approaches 4 of f of x is equal to 2. And you're also given that the limit as x approaches 4 of the function g of x, this is equal to 10. So use the rules of limits to find the following limits. So we're going to find the limit as x approaches 4 of f of x plus g of x all over 4 times g of x. So technically, we're using the rule of limits that if we have a limit of a rational function, we can take the limit of the numerator and the limit of the denominator. I'm just going to write this out showing the steps, but these are the reasons why we can do this. You can probably show this without going through all these steps. So we have the limit of the numerator all over the limit of the denominator. Then we can use the other rule that says if you have a limit of a sum of functions, then we can look at the limit of each function. So this is the same thing as the limit as x approaches 4 of f of x plus the limit as x approaches 4 of g of x all over. And then there was another rule that says if you have a coefficient times some function, you can bring that coefficient out front. So this is the same thing as 4 times the limit as x approaches 4 of g of x. But we're given what the limit as x approaches 4 of f of x is, and so that's 2. So this piece right here is 2 plus, and then we also are given the limit as x approaches 4 of g of x, and that was the 10. So let's just go back in there and plug it in. So we have 2 plus 10 all over 4 times 10. We want to simplify. So 2 plus 10 is 12, all over 4 times 10, which is 40. They both have, what do they both have in common? They both have a 4 in common. And so this is equal to 3 all over 10. Okay. say you have a piecewise function, f of x. So it has two separate equations. The first equation is 5x plus 3. And we're going to use this if x is less than or equal to 0. And the second equation is x squared minus 2x plus 3. And this is the case if x is greater than 0. Okay, so first asked to choose the following graph, but you should be able to graph this. So when we're graphing piecewise functions, you're graphing each separate piece, but you're not using any x values that aren't in the domain for that equation. So each piece is going to stop or start at a particular value. And so the first equation, it tells us that we're using this when x is less than or equal to 0. So when we're graphing these, we always want to graph the value where it's changing or is the end value of our inequality. So 0, we want to see what's happening at 0. If we plug in 0 for x, we get 5 times 0 is 0 plus 3, so that's 3. So we have a point at 0, 3. And because it has the equal to part on that inequality, it's a solid circle. I am not going to choose any numbers that are bigger than 0 for this equation. So if I chose a number that's smaller than 0, so let's say -1, and plug it in here, well, 5 times -1 is -5, and -5 plus 3 is -2. So at -1, I have a point at -2. And now this is linear, so this is just a line. So it would just be shooting downwards like this forever. So I also want to graph x squared minus 2x plus 3. And this is for values of x which are bigger than 0. Even though it's not included, when x is 0, it's the end value of the inequality. So we need to plug that value in and see what we get back. So 0 squared minus 2 times 0 plus 3, so this is 3. So normally I would go in and put an open circle there, but I noticed that this is also the value that was a point from the equation above. And then any number that's bigger than 0, we would plug in. And I also know this is a quadratic and it's a parabola shape. So let me just get one more point. So 1 squared is 1. 1 minus 2, so that's -1, and -1 plus 3 is 4. -1 plus 3 is 2. Okay, so I noticed this dip down, and I know that my prow has to face upward, so it's probably going to turn around. So let me just do one more point. If I plugged in 2 in there, we get 4 minus 4 is 0. So 2, 3 is also a point. Okay, so we got the graph. Select, so is this graph discontinuous, and if so, where? Well, 5x plus 3, that's a polynomial. Polynomials are continuous everywhere. Same thing with x squared minus 2x plus 3. They're continuous everywhere where they're defined or given the domain. The only problem we would have is this in value of the inequality. And because the left and the right-hand side are the same values, the limit exists and it's equal to f of that number. So it's continuous everywhere. And so we're just going to say as the limit as x approaches 0 of f of x on the left, which was the 5x plus 3, this was the same thing as the limit as x approaches 0 from the right, of x squared minus 2x plus 3. Which in this case, you should also know, is equal to 3. Okay, so we also looked at piecewise functions before and trying to find some variable, the value of some variable to make the piecewise function continuous. So it says the following. Find the value of the constant k to make this function continuous. And so again, we have a piecewise function, and they name it g of x. And this is equal to the following. So the first equation, in the numerator, you have 2x squared minus 3x minus 20. And then all over in the denominator, you have x minus 4. We're using this equation if x does not equal 4. Where you're going to use the equation kx minus 7 if x equals 4. So how are we going to solve for k? Well, g of 4 here, by definition, when x is 4, we use the second equation, right? And so using this second equation, we would have k all times x, which is 4 minus 7. So this is equal to 4k minus 7. This has to be the same thing as the limit as x approaches 4 on the left and the right of this in order for it to be continuous. If we looked at the limit as x is approaching 4, of this 2x squared minus 3x minus 20 all over x minus 4. So go in and plug in 4 wherever you see an x. We got 2 all times 4 squared minus 3 all times 4 minus 20 all over 4 minus 4. So 4 squared is 16, and then times the 2 out front is 32, minus 3 times 4 is 12, minus 20, all over 4 minus 4 is 0. Well, 32 minus 12 is 20, and 20 minus 20 is 0. So we get 0 over 0. So the problem is that there is an open hole here. And so we're trying to fill in that open hole. If we didn't get 0 over 0, we would actually have an asymptote at x equals 4, and there would be no way to make that continuous. So basically, this is telling me this numerator factors, and that factor is going to cancel with that factor x minus 4. And so I have to figure out how to factor that. And so let's just look at that. So I can use my AC method and do it that way. I can do trial by error. Well, I have a 2x. Well, I know, right? We probably have to get this x minus 4 factor for this to work. So let's put that up here. And so really all we have to worry about is that last term being negative 20. If I multiply something by negative 4 to get negative 20, this would have to be a plus 5. So let's just make sure that's right. So 2x times x is our 2x squared, so that's good. Our middle term would be this negative 8x, 2x times negative 4, which is negative 8x, plus 5x. Negative 8x plus 5x is our middle term. Okay, so we got that. And so notice that these cancel. So now if we look at the limit as x approaches 4 and go in here and plug in 4 wherever we see an x, we get back that this is 2 times 4 plus 5. Where this is equal to 8 plus 5, which is 13. So in order for g of x to be continuous, at x equals 4, then we know that the limit as x approaches 4 has to exist at g of x, and it has to equal g of 4. Okay, well, we just found what that limit was, right? We just found that limit was 13. So we know 13 has to equal g of 4. Well, we found g of 4 up here before, right? G of 4 was this. And so we're setting our 13 equal to the 4k minus 7. So let's just solve for k. So if we add 7 to both sides, we get 20 is equal to 4k. Divide by both sides by 4, we get k is 5. So find the value of k in order to make that continuous. Okay, so we found out what k had to be in order to make that function g of x continuous. And so technically this would be 5, then x minus 7. So any questions on limits or continuity?
The only question, or the only thing that I would like to go over is when we got 0 over 0, and then we plugged in the 5 into the equation of 2x plus 5 times x minus 4 over x minus 4. How did you get 5 again? What was the process of that?
Are you looking at a different equation or this
No,
equation?
I'm looking at this equation. Once we, for the equation to find x, basically 13, how did you get 5 for that?
Okay, because
You said something minus 20, or
right.
It was like an equation or something.
Oh yeah, okay, so right now, well, we knew that 13, our limit as x is approaching 4 of g of x, we just found was 13, right?
Oh, the one right above it.
Yep. And so, and then we saw up here that g of 4 was this equation for k minus 7. And so in order for something to be continuous, the limit has to be the same thing as g of the number that you're approaching. And so these two things have to be equal to each other. And so all I'm doing is solving for k here. And so I added 7 to both sides of my equation to isolate the term with the k. And so I have that 13 plus 7 is 20 equals 4k. And then divided both sides by 4 to get k was 5.
Right above that one where it says limit x equals 4, then the equation is in parentheses 2x plus 5.
Yep.
Where did you get the 5 in that one?
Okay. Now I see where you're.
Sorry.
No worries. So I'm factoring the numerator. And so because I got 0 over 0, that's going to really basically tell you that one of the factors in the numerator is the same as the factor in the denominator. So I just use that fact to help me. But if I didn't see that, there's a couple ways that we can go about factoring this. And I normally go about using the AC method and rewrite it doing grouping. So there's an AC method that says if this is not 1 in front of the x squared, when you're factoring, look at this a value times your c value. So 2 times negative 20 is negative 40. So you're trying to find two numbers that add to this number, but would add to not add to that number, would multiply to that number, but would add to the middle term.
Okay.
And so going through that, this is how I would get the factoring. And so those two numbers that would add to negative 3 and multiply to get us negative 40 are 5, all right, and negative 8. That's where you got to go rewrite this factor, 2x squared. So this is minus 8x plus 5x is another way to write that middle term as negative 3x. Minus 20. Factor by grouping. Pull out a 2x, we're left with x minus 4. Pull out a 5, so plus 5, I'm left with x minus 4. That x minus 4 is the same, which should be the same if we did this right. And then what's left would be that 2x for the first piece and the plus 5 for the second piece. And so the factored form is this. So the other trick I was saying, or why I knew it was 5 there, is again, because I knew that factor was x minus 4. And so what would multiply to get me negative 20 here would have to be a 5. And what would multiply to get me a 2x squared? Well, if this has an x here, this one would have to be a 2x. So I kind of just did it by trial, kind of by guessing, and then just making sure I had chosen the right things.
Okay, thank you.
You're welcome. Any other questions? So rates of change was the other things that we looked at. Secant line that got us into the average rate of change going down and doing that limit as h approaches 0 really small, and getting the instantaneous rate of change, finding equations of tangent lines, secant lines, all ringing bells to you guys, hopefully. So it would be nice if this was together, but it's not. Okay, so using the definition of derivative, here we go. So use the definition of the derivative. So you guys know the faster way right now. So you can use that faster way as a check. But when I test you on this, I will probably test you on doing one of these when you're taking it, when I say in class via Zoom. So that was the limit as h approaches 0. We're looking at f of x plus h minus f of x all over h. And they give us that our function f of x is negative x squared plus 3x minus 6. So you can do it in pieces if you want, but first thing that we're looking at is this f of x plus h. And so we're going to go in and we're going to plug in x plus h, this whole thing, wherever we see an x in here. So let's just do that. So we have minus, you see an x, so we're going to put parentheses, we're going to square that, plus 3, you see an x, let's put parentheses, minus 6. And so inside those parentheses, we're plugging in x plus h. Then it tells us to subtract off, so minus your whole function f of x. Well, our whole function f of x is this. So minus this negative x squared plus 3x minus 6. And then we put it all over h. So if we clean things up and we multiply out x plus h times x plus h, you would get back x squared plus 2x plus h. Sorry. You get x squared plus 2xh plus h squared. If you distribute that 3 to the x plus h, we get plus 3x plus 3h. Bring down our minus 6. Distribute your negative. So we get, what is it, plus x squared minus 3x plus 6. Okay, so things normally clean up really nicely. We need to also distribute this negative. So we have a negative x squared minus a 2xh minus an h squared plus 3x plus 3h minus 6 plus x squared minus 3x plus 6. When we have a negative x squared and a positive x squared cancels. We have a positive 3x and a negative 3x cancels. We have a negative 6 and a positive 6 cancels. So notice all the terms that are left in our numerator have an h. So we can pull an h out and cancel it with the h in the denominator. So if we do that, we have the limit as h goes to 0. We pulled out an h from the negative 2x and canceled it with that. So negative 2xh. So we're left with negative 2x. If we pull out an h from the negative h squared, you're left with just a single h. And if we pull out an h from the 3h, we're left with a 3. And we canceled it with the h on the bottom, so we're left with 1, and we don't have to write it. So when x goes to 0, h goes to 0, we're left with negative 2x plus 3. Okay, so you guys should know that, now looking at our original, which is this, and using our general power rule, right? If f of x equals, let's just show it, negative x squared plus 3x minus 6. Our general power rule says bring our power down front. Oops. Bringing our power down front, we have that negative still. 2, subtract 1 from our power. We get 2 minus 1 is 1. Plus, bring our power down front of 1, that's just 3. And that goes, square root of x is 1, sorry. And the square root of negative 6 is 0. Which is the same thing we got here. We just had to use the formal definition. I don't know why I jumped. So because you know that general power rule, knowing and doing, you can check it really easy and see if you had done any errors in there. So if it wanted then to say, what is f prime at a particular number? We can find f prime at any number now because we did it this way. So f prime of 1. So that just tells you, right? You're going in wherever you see an x, you're going to plug in 1. So we have negative 2 times 1, which is negative 2. Negative 2 plus 3 is 1. So if it asked find the equation of the tangent line, at x equals 1. Well, we just found our slope. F prime of 1 was equal to 1. And so our slope of our tangent line is going to be 1. We need a point. On the line, and we can find that point because we have the equation. So we can find f of 1. So that was negative. You had an x squared, so let's just put parentheses. What was the other equation? So it was So let me just look at it instead of guessing. Plus 3 times x. So plus 3 parentheses and then minus 6. Oops, it was right here. So we got -1 plus 3 minus 6. So -1 plus 3 is 2. 2 minus 6 is -4. So we have a point. And so we can figure out what b is by plugging in our x and our y value and our slope into the slope-intercept form. And so our y value is -4 is equal to our slope, which is 1, times x, which is 1, plus b. So -4 equals 1 plus b. Subtract 1 on both sides, we get b is -5. So equation of the tangent line y equals our slope, which is 1, times x plus b, which is -5. Okay, so I was just throwing a couple different things in one different problem. So you should be able to do the formal definition. Sorry, trying to get it all on one screen so you can see it. You should be able to use a formal definition to find the derivative. You should be able to find the derivative at a particular value using the formal definition. You should be able to find the equation of a tangent line at a particular value. Oh, I think this is a good spot to take a break.